Hi, Lisa McPherson with A Plus College Ready, here with the Unit 4 multiple choice practice questions. These are the questions that appear at the end of the Unit 4 PowerPoint. These are not the same as the practice questions that are seen elsewhere in the unit material. This video is intended to be played in the classroom, and you pause at the end of each question, allow the students to submit their answers either electronically or on paper, however you wish to choose to do that, and then the next slide will have the answer, and I will do my best to explain that answer to that question. So let's start with question number 1. Naturally occurring copper is composed of two isotopes, copper 63 and copper 65. If copper is 69.1% copper 63 and 30.9% copper 65, the average atomic mass could be calculated as, please pause and choose your answer. When everyone's had a chance to answer, come back to the video and we'll talk about what that answer is. So first I want to point out that the first obvious wrong answer is B. And the reason for that is that here this is a simple average. And a simple average would only work if each one of the copper isotopes 63 and 65 were represented at 50% each. Since they are not, B cannot be the right answer. The problem with C is that the percentages have not been changed to their decimal equivalents, and that needs to be taken care of. So A and D are our most reasonable answers, and as it turns out, D is the correct answer. We do not divide by 2. That would be assuming, again, a 50% distribution. That's sort of putting both kinds of averages simple and weighted together. So D is the correct answer. Question number 2. The photoelectron spectra show the energy required to remove a 1s electron from a nitrogen atom and from an oxygen atom. Which of the following statements best accounts for the peak in the upper spectrum being to the right of the peak in the lower spectrum? Pause. Choose your answers. So the first thing that I need to bring your attention to is the question says, show the energy required to remove a 1s electron, not valence electrons, but this is the 1s electron. So there are no shielding electrons. These are the electrons closest to the nucleus. And so they then say in the real question that they wanted to say want you to state which of the statements accounts for the peak in the upper spectrum being to the right. Well, what does to the right mean? So you have to look at their binding energies, which is just another way of saying ionization energy, the amount of energy that's required to remove or break off that electron from the nucleus. And notice that nitrogen's electron, its binding energy is what? Less than oxygen's. Why would it be easier to remove a 1s electron from nitrogen than from oxygen? Well, let's take a look. The answer is D. The effective nuclear charge for nitrogen is only 5, whereas the effective nuclear charge of oxygen is 6, because remember the ZEP is equal to the number of valence electrons for elements in the main group where the S and the P blocks. And since the effective nuclear charge for nitrogen is less, it means that it requires less energy to remove that electron. And we don't even need to think about effective nuclear charge here because they are 1s electrons. It's just whatever the absolute of nuclear charge is. And it is 1 less for nitrogen than it is for oxygen. Question 3. An element Z has the electron configuration xenon 6s2. The oxide of this element will have which formula below? Okay, so you can take a look at the periodic table and you say 6s2. We don't even need to know for sure, but it turns out that is barium. But what 6s2 tells us is that we have an element that's in the s2 position, so it's got 2 valence electrons. And a metal is going to lose those 2 valence electrons and form a +2 ion. Well, oxide, the oxide ion has what charge? -2. And so +2 and -2, that should form C. Question 4. Of the following, the species that has the correctly predicted largest radius is what? Notice we have a neutral atom, and then we have 3 ions. Pause, choose your answer. So let's take a look at where these 4 elements are on the periodic table. Argon and bromine are relatively close to each other, but bromine has one more energy level. And actually that bromide ion has the electron configuration of krypton. So it is larger than argon because it has another energy level. Compared to potassium, well, potassium is in the same energy level as the bromide ion, but it is the potassium ion, and it's lost that energy level, so it really has the electron configuration of argon. And then strontium is also in in another period greater than bromine. It has an additional energy level. However, because it's the strontium ion, that means that that energy level has now been taken off, and this is isoelectronic with krypton. So we've got to think about what's happening with these, but remember, the big thing to remember here about largest radius is we said that typically anions are going to be larger than cations because we're adding electrons, and that's causing the electron cloud to swell because of repulsive forces, whereas cations are losing entire energy levels. And because bromine has another energy level larger than argon, our answer is going to be bromine. This was not this answer is not one that I've written. This came from another presentation. I have some issue with saying decreased effective nuclear charge because the bromide ion really has quite a large effective nuclear charge, so I would probably dismiss that in this case. Now, question number 5, the observation involving the first ionization energies of oxygen and nitrogen is best explained by which of the following? So let me tell you what they're after here. Notice that we're going from lithium to neon. That is working across the period in period 2 of the periodic table. And we said that for first ionization energies, those ionization energies increase from left to right across a period. So we can see that trend here. However, we have a couple of places where we have a decrease in first ionization energy, so we're going against the trend here, and that's what this question is really asking us. It says, hey, why this decrease in first ionization energy between nitrogen and oxygen? So this one's going to take a little while for you to work on. There's a lot of reading here, so take your time and then come back when you're ready. So let's jump to the answer, and then we're going to come back and talk about why it is the answer. So the answer is B. Comparing electron configurations of oxygen and nitrogen should allow you to see that oxygen has paired electrons while nitrogen does not. So what does that mean? Well, let's look at B, repulsion between the 2 paired electrons in the oxygen orbital. Well, what they're really talking about here, and pardon my drawing, this is not going to be lovely. If we're looking at the 2p sublevel here for oxygen and nitrogen, for nitrogen, we're going to see that it ends in 2p3, and we have those 3 electrons. None of them are paired. But for oxygen, we're going to add in this 4th electron there. And notice we have electrons paired here. And because these electrons, this is what I was talking about before, electron-electron repulsion, these 2 electrons in the same orbital are really repelling each other. And that's going to make this second electron easier to remove than you would normally expect. So notice we say successive electrons are harder to remove except when they're not. And the reason this one is not is because that extra repulsive force inside this individual orbital causes that particular electron, which is the first one that would be removed, first ionization energy, that's going to be the easiest one to remove, and it's easier to remove than, say, this one for nitrogen, because that one doesn't really want to go. It's fine, not being repelled by anybody. But that one is, there's our reason. Now let's look at why A, C, and D are not our best choices, okay? After I erase that, okay. So differences in electronegativity between oxygen and nitrogen cause first ionization energy of oxygen to be less than nitrogen. Well, let's just state here, electronegativity doesn't have anything to do with first ionization energy. Electronegativity is the how strongly an atom, when it is covalently bonded to another one, attracts electrons in that covalent bond to itself. Well, we're not talking about bonding here at all, so electronegativity is out. C, greater effective nuclear charge in nitrogen than in oxygen causes first ionization energy to be less. Well, okay, stop. Effective nuclear charge is not greater in nitrogen than oxygen. Zeph for nitrogen is 5. Zeph for for oxygen is 6. So C is just a false statement. D, greater atomic radius in nitrogen than in oxygen causes first ionization energy of oxygen to be less than nitrogen. Well, is the atomic radius of nitrogen greater than oxygen? Yes, it is. First part of the statement's true. But if you have a larger radius, that should make electrons easier to remove. And it says the first ionization energy of oxygen is less than nitrogen. If oxygen had a smaller radius, its first ionization energy should be greater, not less than. So those two statements don't really go together in D. Okay? So again, B is our correct answer. Just a little bit confusing. Number 6. Which of the following elements would have the largest second ionization energy? Pause. Choose your answer. Okay, so largest second ionization energy. So we're looking at successive ionization energies here. Remember, we had that table and we had the stair step that separated first and, or successive ionization energies where there was a huge jump. So if you are going to have a very large second ionization energy compared to your first ionization energy, you would probably suspect that you would have only one valence electron. Having said that, our answer is D. While both hydrogen and potassium have one valence electron, only potassium has more than one electron. So again, let's go back to that. Hydrogen only does have one valence electron, but once that valence electron is gone, all you have left is a proton in the nucleus. There are no second electrons to remove, so it can't be hydrogen. Fluorine has 7 valence electrons, sulfur 6, so they wouldn't have really large second ionization energies. They would be larger than their first, but not a really giant increase. But potassium, once you remove that first valence electron, you've now stripped off that outer shell, and you now are down to an inner core electron is going to be the second one you're removing. Much higher second ionization energy than first, so our choice is, of course, D. Talking more about successive ionization energies here, we have some listed for element X in the table. On the basis of this data, element X is most likely to be what? Pause. Choose your answer. Okay, so let's take a look. First ionization energy, 580 kilojoules per mole of electrons removed. Second, an increase, about 3 times as much. Third, another increase, and this is not quite double. And fourth, wow, That's a lot. That's 4.5, 5, almost 5 times larger. And then we have another modest increase here. So our big jump in ionization energy happens here between our third and our fourth ionization energies. What does that mean? It means that we have 1, 2, 3 valence electrons. These, the fourth and fifth, are inner core electrons, much harder to remove. And so which one of our elements has 3 valence electrons? Correct. Aluminum. Okay. This is the end of our practice multiple choice questions. Video 5 will cover free response practice questions.